Baby, you give me ice and fire. You're giving me wind and rain. You're some kind of butterfly. Baby, you.
Hi everybody, in this video we're going to do a rundown on the liquid cooling for my electric motor.
You whip up my appetite. Don't leave me here high and dry. Oh.
Hey everybody, I've got all the parts here so far for my cooling system. So I'm just getting ready to assemble, and I thought I'd just sort of go over this a little bit. So the first step is this cooling plate. So this cooling plate is almost the same size as my controller. And I'll show you the controller here in a second, but basically the cooling plate will go under the controller, and I've got some thermal paste which will go between the controller and the pad, so if there's any grooves or anything, I'm basically going to sandwich that on here so that it makes a good contact with the pads. And I got this cooling plate about an inch bigger than the height of my controller, and the controller is just a slightly longer.
Some kind of butterfly. Baby, you give me midnight. You whip up my appetite. Don't leave me here high and dry.
So that way I can put the screws in of the controller, and then I can screw this plate into the aluminum backing plate. So basically I effectively have a heat transfer shield that's directly underneath, occupying probably about 95% of the size of the controller. So that's the first step. And then you can see there's a couple of hoses. So I'm going to have the hoses then connecting over to this radiator. And what I decided to do is I decided to get a radiator from a high-performance computer. And the reason for that is I just had all these parts kind of readily available to me more than anything, but you can kind of use any radiator and fan. You just need some way to get heat dissipation. So I'm going to, this is a 3-fan model, and essentially you use these 12-volt computer fans. So everything is going to be exactly 12 volts, and I got quiet fans with ball bearings, so these things should last really quite a long time. So there's 3 fans that goes along the radiator, and then the tube will go from the cooling plate into the radiator and get cooled. And then the other end of this goes into this pump. So this pump here will receive the incoming cooling. I'm just going to be using a glycol mixture. I've decided to buy this tank. You don't need it, I don't think, but it's mainly for allowing air out, ease of access. So again, being a computer part, it's all the same size tubing. So it matches the tubing from this, it matches this, it actually matches my electric motor. But I'm going to leave the electric motor out here, and I'll talk about why that in a minute. But essentially, you drop the cooling into here, the pump goes, and you pump the cold water back into the cooling plate. So the circuit will be, it gets heated by the cooling plate, goes through the rad, fans are turning, blowing air through the radiator to cool it, and it then comes into this high temperature pump. This pump can do, it's rated -40 or something to plus 140 Celsius. So it's particularly made for computer, or for high temp. And it has a certain amount of volume of liquid up here, which you could pretty much use what you want. But the only reason why I have this again is just to, when I'm bleeding it, I can take the screw off the top without having to dismantle everything. And it'll give me a visual cue as well, like is this stuff getting dirty or not, this glycol mixture. So anyways, that's the closed loop that I'm going to be creating with this. So I'm just going to assemble the fans on the radiator, and then I've got to find a place in the back where this is going to fit within a reasonable distance. This pump can do 3 meters of elevation, so it should be plenty strong to keep things circulating. And you don't want things to go too fast, so you want some amount of resistance in here so that it takes time for the pump to pump the cold liquid or the liquid through the radiator. That's necessary. So because if it goes just blaring through there like max, and I don't know like if your heat dissipation, so you want it to get a little bit hot and then give the fans a chance to lock it down. But anyways, I think by default we can do this. Otherwise, I'm going to have to put a little bit of a flow regulator into the tubing, which is, like I said, pretty easy to do. Just put something like a little gate valve, and I can adjust the flow that way, or adjust the power. I could do it that way too. So anyways, I just picked up this from, what do you call it, online. I got the fans from actually mining equipment, and this was for a cooler for a computer. This I had to buy from an electronics distributor, specifically for the sizing that I was looking for the cooling sink. So over here, just to show you where this is going to go, this is the plate or the controller where the cooling plate will go. I'm going to leave this elevated on top like this because I actually have room on the back to put a heatsink. And if I put a heatsink, I have the fan right now in behind, but my goal is to get rid of the fan so I don't have to, but I technically could put a heatsink in addition, which might be able to help out as well, the heatsink. So I'm looking at putting down below here the pump, or maybe under the wires or over on this side. I'm not sure. Maybe this side makes more sense. And the radiator, I've just got to find a spot to put it. And then my stairs, right now I've got kind of like an enclosed stair, so it's not going to be very helpful at all. But I had my design here is actually to get rid of all this, so that I wanted to make the stairs a little taller and then open, so that way I can create more heat dissipation by more airflow. This blocks pretty much all the airflow when it's in here closed. But what happened was that when I was doing my motor testing with the heat and running this, this thing gets to 100 degrees like right away. That's the thing that gets the hottest the quickest. The motor, after an hour of testing, like changed from 30 degrees to 40 degrees. So basically the ambient air temperature on the day I tested was 30 degrees, 33 out actually. And that's exactly the temperature of the equipment. So this right now is sitting at probably 28, because today's 28, without it being on. So it heated, it took about an hour to heat up to 100 degrees without the fan. And then this one here, my electric motor, in the same period only went to 40 degrees. And I realized now, after looking at the settings, is that the settings for temperature in the VEC 500 are actually referring to the controller. I'm almost positive, because I saw the controller cool down, but it kind of goes, there's a level 1 stage, a level 2 stage, and then it shuts off. And it went into level 1 stage where it lowered the speed to try in an attempt to try to cool it. So that's the setting in the controller, and they call it motor temperature, but it's not the motor. It's actually the temperature of this unit, not the motor. The motor was at 40 degrees. This was at 100 degrees when it shut off. So I don't think I'm going to put the cooling through the motor. I still want to run some tests. I might put through anyways, who knows. I'll just check what the temperature of the cooling is once I get the fans going, to see how well the radiator actually cools the fans. Otherwise, what I'm going to do is I'm going to make a separate system just for the controller, so that I don't take hot water and push it into a colder device, because then it'll actually just artificially warm up that device. So as a first test, I'm going to put the cooling unit here. I'm going to keep the electric motor out of the cooling, the liquid cooling of the motor out. Because like I said, I went with the temperature sensor and everywhere on this unit, and it was only 40 degrees. It was easy to touch. Whereas this gets extremely hot, this controller plate. So I'm pretty confident that putting in this cooling plate and the liquid cooling on the radiator system with the high temperature pump is going to help relieve my cooling issues, which I never had for 2 years until I got these lithium batteries, and now I can push more than 25 amps So let's see here. So like 25 amps works out to, I was probably running around 600 to 800 watts to get my boat speed anywhere I was going, basically. Maybe 1200 at the most, and I'd drive out, and I don't drive far enough to warrant hitting that. But with the lithium batteries, like I said, I've been more liberal with my power, and then I've never encountered this overheating problem. So it's the amp draw that you're pulling that creates more heat for the controller, because it has to convert that energy from DC to AC for the motor. Even though it's a DC brushless motor, technically the stator is AC. It's a sine wave to create the phases. So that's actually why there's heat. It's because the controller has to take that and then set the phase of the waves on the three-phase motor to be timed properly to push the motor around. That's actually what these are here. So if you've ever looked at the motor, there's 3 wires on the top, and the reason for that is that's phase 1, phase 2, and phase 3 for the 3 phases, and the controller has that same setup. So the controller phases a sine wave, and 1/3 of it is here, 1/3 of it is here, and that's how it turns the motor using magnetic induction. That was the 10,000 foot view explanation on electric motors. Anyways, just wanted to pass that on, that I'm getting ready to get this installed, and those are the components, and I'm looking forward to running a test. I should be able to get this, I think, by tomorrow, plugged in, and then I'll just run some 12-volt line over to something, or piggyback off of something, just so I can get this thing working with a simple little switch or something. I'll figure it out. Anyways, I'll next see you when I have this thing ready to test.